before. Okay. Yeah, thank you very much for the wonderful introduction. Thank you very much for inviting me. A special thanks goes to Adia Labs, Horst and Amelie for having me here. I'm very glad that I made it here. In fact, it has been an amazing trip so far. Probably most of my most exciting trips, definitely this year, but probably also last year, because it's raining in Abu Dhabi, and that caused a whole lot of disruptions to my travels. I don't want to go into all kinds of details, but for me, it was a big honor to yesterday be at an event in Dubai in the context of the World Governments meeting, where Jensen Huang and your new Minister of AI was actually were speaking on a fireside chat. And I personally learned a whole lot. And the most important thing I learned is about the local economy and the way it works in this country, where many of the things seem to be depending on AI, on science, on the latest, greatest technology, which is quite encouraging. And I really want to applaud you for having an AI minister. So that's probably the most amazing thing. So I'm Torsten from ETH Zurich, and in my research, I'm working on very large-scale computing. So I'm a traditional high-performance computing person, as we've just heard, building very large systems. And today, all of these very large systems are really about artificial intelligence. So the largest systems on the planet today are built to train very large language models. And I want to take you on a tour through all of these optimizations, all of these techniques that you have to implement. And I'm saying have to, because it enables new science at new scale in order to get there. So it's going to be a very technical tour. I'm going to go into lots of detail, lots of technical detail. If you have any questions, interrupt me anytime. I'm a very interactive speaker. I quite enjoy being interrupted. No worries. I will make sure to stay within the allotted time, so I will not run much over. Okay, so let me get started. And now it's actually refusing to get started. So I press that button. It's probably not in focus. So can you just, yeah, exactly. So let me get started and start a little bit more on the general AI introduction, which probably most of you know. I mean, if you haven't been living in a cage, in a cave for the last 3 years, you know what ChatGPT is. And ChatGPT is actually quite an amazing product in some sense, because it has been shown that it could in fact be your lawyer in the US. It could actually also be your business administrator in the US. So it would pass the exam to lead there. It could be your doctor. And in fact, it would show that it's very likely that you would actually prefer it as your doctor. Like 71% of the, actually 79% of the people in this study preferred ChatGPT over their real doctor. So there's a huge, a huge opportunity. The main reason, by the way, why the real doctor was not so preferred is it written here? Well, it's because of empathy. So if you've actually worked with a chatbot, these chatbots are overly empathetic, so much more than real humans. It's quite interesting. Also, it could be me. So ChatGPT could actually just replace computer scientists at the end, and is probably going to replace big parts of computer science. So now the question is really, it's a philosophical question that we can discuss over the apero. What is left for us humans? So what do we actually, what are we good at? Well, what we are really good at and what makes us special, if you go back to 2016, which was before the time of AI, is what differentiates us from the closest thing to humans in 2016. These were chimpanzees. Today, I would argue the closest thing to humans is a language model. They're actually much closer than chimpanzees, because chimpanzees would not pass the Turing test. Language models would. But at the time, they basically list all kinds of things, which both of these things apply to language models. There's one thing that doesn't really apply. So it's called theory of mind. This is a very important concept that humans have. And if you think about it, theory of mind, which is really the ability that I can connect to you, that I have a model of what's going on in your brains, that I can efficiently communicate to you because I have this model of what's going on in your brains. I hope I haven't lost everybody yet. So, and that is theory of mind capabilities. So I can understand what other people think. And now, do language models have theory of mind? So can language models actually form groups? So why is theory of mind so important for humans? Because it enables us to collaborate. If we wouldn't have theory of mind, we would not be able to work with other people. We would not be able to build buildings like the one we are standing in, because no single human can build these buildings. We would not be able to build computers or airplanes or anything. So, well, in 2023, about 1 year ago, ChatGPT was shown to have theory of mind capabilities. Today, it actually has theory of mind capabilities that are about as good as the average human has. So it's going to be more interesting. So just as an outlook, going a little bit closer to today. Just last month, this person, and I don't want to introduce, or I don't have to introduce this person, was actually making a quite outrageous statement. So he said that by the end of the year, we, which is the company Meta, will have about 350,000 NVIDIA H100 GPUs, or about 600,000 H100 equivalent in compute power in the company. So that is a company that is known for social networks. And they now throw these numbers, and he didn't make a large announcement about this. It was basically just mentioned on the site. So I'll get a lot of GPUs here. But if you actually look at this, what this means, okay, this is a press release. It's $18 billion worth of compute. So if you think about it, in the good old days, large companies were buying other small startup companies to make a big business. Today, large companies are buying compute power as an investment into the future to make a big business. And that is a huge change. So compute power itself is now more important, more expensive than human power, because these models can replace humans in many, many, many ways, or take work off humans. So this is something that I find rather fascinating. And actually, if you go back to the good old field where I'm coming from, also Horst was a co-founder of the top 500 list, the fastest computers on the planet. So how many top 500 list is the compute power that Meta is going to have at the end of the year? So Horst, you should know. So is it 0.1, 0.5? Is it one top 5? And I mean all of the 500 fastest computers on the planet combined, the sum of those. Is it 10 times? Do you have anybody? If you're experts, yeah, you're good. We have 8 exaflops of FP64 performance in the top 500 list today, like if you sum it all up. If you now go forward, do the math with these Hopper GPUs, you'll get to, depending on how you count, you'll get to somewhere between 5x and 7.6x. So the 10 is pretty good. That is completely crazy if you think about it. A single company wants to own 5 times the combined compute power of the top 500 computers on the planet. This is a little bit fishy here, so we can go into this, but make it at least 4. Okay, so we can talk about this in detail. Okay, but that gets me to the real point of that talk. So artificial intelligence. If we go back to the 2018 Turing Award lecture by Geoff Hinton and Jan LeCun, they both really they have 2 important quotes. One is really the deciding factor for the AI revolution was the increase in compute power. So it is about the compute power. It's not new algorithms. We're using the algorithms that existed in the 80s. It's compute power and, of course, data. And a lot of credit for deep learning goes to the people who made computers go fast. So now the question is, who are the people who made computers go fast? Well, in computer science, we have a way to reward these people with the Turing Award. So 2018 Turing Award was given to the Kuhn, Hinton, and Benji. Well, who made computers go fast? Jack Dongara, 2021 Turing Award. He's actually on the Adia Labs advisory board, so you're very well connected. And thanks to his work, much of these supercomputers are more than 70% efficient for specific workloads that are very important for AI today. So now if we go a little bit into the past, in 2019, I spent my sabbatical at Microsoft, and there was a very, very secret project at the time, which you can read about here. Now it's all public. We know all about it. August 3, 2019, Greg Brockman made this statement: "We think the most benefits will go to whoever has the biggest computer." Greg Brockman, the CEO of OpenAI, now his is it CEO or CTO? No, I'm a bit confused. So anyway, one of the co-founders, Sam Altman, just asked for $7 trillion to revolutionize that business, right? And I know he's been here. So keep that in mind, right? So it is and again, we think the most benefits will go to whoever has the biggest computer. That is the key to OpenAI's success, right? They're going there. Okay, now let me explain a little bit more how AI actually comes into place. We're still in the motivation section. So now the funny thing is supercomputers used to be only limited to people running scientific simulations, like large-scale weather simulations, building planes, building buildings, building all kinds of things. And today, companies like Facebook or Meta build supercomputers. Actually, Tesla, a car company, builds a supercomputer. In fact, they build a supercomputer where they design their own chips and their own network, the Dojo chip. Like, so this is somewhat crazy. Google, a search company, builds supercomputers. Microsoft, where I was there, $1 billion investment into a supercomputer program, which at the end created ChatGPT. Right. So this is the major thing. They even make comics about supercomputers, so it must be really cool in some sense. But how does this now work? So what do we talk about? What is the workload we really want to talk about? I want to give you a 10,000-foot view. I can go into arbitrary detail, but again, I only have 45 minutes to present the whole thing. So, but the way it works is relatively simple. So we take text off the internet, just random text. And the goal is to train a language model that can emulate humans. What are humans? Well, in my view, humans are very close to statistical language models. I'm speaking to you, I'm connecting to you through language, through spoken language. And you have a certain expectation what I'm going to say when I started a sentence. I'm not changing this in the middle. So the statistical distribution of language is actually the representation of all of human knowledge, because all of the human knowledge is encoded in language. That's the only way I can communicate to you. It's language. So that is our fundamental form of knowledge encoding. So if I can learn, I can train a model that can deal with language and knows about all of the statistical properties of language. It encompasses all of human knowledge. Right? That is the power we have. So where is the human knowledge stored? Well, in the internet. So that's the first approximation, right? So where do I get most knowledge today? From the internet. It's not an encyclopedia anymore. It's the internet. So I take data off that internet. And now how do I learn the statistical distribution of this data? Well, I take a sentence. I remove a piece of text in that sense. It's actually super simple. It's super simple. Like here, this word is missing, and you can all guess what it means, what should be there. Then I run it through a computational structure that is literally a function f of x. This is x, and x has missing an input. And I ask this function f of x to predict the statistical likelihood of the missing word. I'm putting all words of the English language here. Like 50,000 approximately. Here I'm just having 5 because otherwise you couldn't see it. Well, it's not even 5, it's like 7 or so. But imagine all of them being there, and then I get a likelihood. So you see not is 0.74%. Of course, I know which word I removed, right? Because you removed it in the first place, you can just remember it. What you do then is you do a layer-wise weight update for this model in the middle. That's my statistical language model. That's ChatGPT, or to be more precise, that's GPT-4. And then I do this over and over again. So now this sounds very simple. Why do I need a freaking supercomputer to do this? I could just do this on my cell phone. Well, wait. GPT-3 was trained with 500 billion tokens. 500 billion is a very large number. They ran a lot of text through that model. And soon, actually today already, it's the whole internet that we use to train these models. Every single thing. This talk that I'm giving right now is going to be recorded. I hear it's going to go on YouTube. I'm 99% sure that some language model is going to learn from what I'm speaking right now in the future. Right? So think about it. We have a lot of cameras here in the UAE. So all of that will go into models that learn from these interactions. So we have a ton of sensors. It's not just language. Furthermore, of course, to deal with all of human knowledge, you need a model that has a lot of capacity to deal with that. So the model that I'm talking about is GPT-3. That's the last open model. GPT-4 is not publicly announced. That model has 175 billion parameters. That's a lot. A billion is a lot. And just to give you some number, it's actually 700 gigabyte in FP32. So if you store it in FP32, that's a 700 gigabyte weight set of weights. In fact, people store it in FP16, so make it 350 gigabyte. But it's still very large. And it takes weeks to train. It took weeks to train. Actually, today on a very fast machine, you can do it much faster. So large-scale AI is the future, because these very large models, they can represent all of human knowledge. They can represent image and sensor data we are collecting today from all kinds of sources. They need to process at the end terabytes or even petabytes per second of data. So we need to enable this. So we need somehow a principled approach, because otherwise we can't build these very large systems. So I want to go into 3 dimensions of what I would call super learning, because it's learning on supercomputers. One is input-output. We have to read the data. We have to process these terabytes or petabytes per second of data. We have to get them into the system. Furthermore, we have to compute the data. Once we have it into the system, to update the weights, we need to work with the models, as I just described. And the last, but probably the most important, most complex aspect of it, is to coordinate very large clusters with tens of thousands of GPUs to actually work together to train these models. And this is, as I mentioned, much more complex than the remaining two pieces. So I will spend most time on this, how to coordinate a very large number of GPUs, that we actually have a supercomputer and not just a single GPU. Okay, so let me start with I/O. It's a simple one. But let me just start with a little bit of math. If you have ResNet 50, it's an image recognition network. A rather old one. I know some of you are like, well, that's like 5 years old. It's ancient. But bear with me. It needs about 3 gigaflop, so 3 billion floating point operations to run a single inference. 3 times that for training. So if you look at the ImageNet database, we have 1.3 million images. The average size is 115 kilobyte. By the way, I was always wondering what's the smallest image in there. It's this one. It's only 508 byte, and I would not recognize that as a nail, but a neural network does. So MLPerf, if you just look at the result on an H100 today, like a Hopper GPU, I will get 81,000 samples per second processing speed. So how fast do I need to feed data into this? Well, I need 9.3 gigabyte per second random access data for training. Right? So that's just the math I can do based on today's performance of these things, which means I would need 50 SSDs per GPU to stream the data into the thing. Nobody has 50 SSDs per GPU because we found ways to make this much faster. So if you now run this on a very large system, you will need tens of thousands of GPUs. You have a lot of parallel file systems. So Horst can probably sing a song about this. Everybody hates parallel file systems in scientific computing because they never work. And everybody acts as if they work, but they usually don't work. They usually cause a lot of trouble. The nice thing is that in deep learning, there's one trick that we came up with that you can really use to simplify this a whole lot. Because what you always do is you randomly sample in deep learning. But what does randomly sample mean? Well, it means we are starting from a random seed, a truly random seed, but then we apply a pseudo-random number generator to generate the offset for the next seed. Actually, once you have picked your, for the next number, I apologize. Once you have fixed the seed, you can just run this random number, pseudo-random number generator into the future. So you actually know what's coming next. This is a very powerful concept. If you ever deal with randomness in computer science, you should keep in mind that pretty much all number generators are pseudo-random, so they're predetermined. They start with a random seed, and then the sequence they generate, I can compute until the end of time. And this is the fundamental concept that we use in an implementation that we call near-optimal prefetching file system. And no pun intended, it's abbreviated as no PFS. And PFS, some people think it's standing for parallel file system, so it's a little bit of an edgy pun here. But it's very, very simple, and I don't want to go into too much detail. The idea is now that every processor can pre-compute the data it's going to read, and it's going to be a random access pattern, but you can pre-compute the randomness, I apologize. So you fully know about the future. So what you can now do is you can look at the distribution of your data access, and in that distribution, the problem is that there are some samples accessed multiple times. So the same sentence is sometimes fed multiple times into the network just because of the random sampling. And so that is pretty nice because I can now cache those highly accessed samples. So I can adopt a caching strategy to this thing. And at the end, what we get on a real supercomputer like the Pitts-Stein system was the fastest system in Europe for a while. We get a speed up, let me just skip a little bit faster, to the competitor more than 100 times. Right? So just by using that algorithmic trick, on the Lassen system, which is still one of the largest systems in the United States, we actually get a speed up on 150 times, but this is really just an artifact of the biggest configuration we ran on Pitts-Stein was 256 GPUs, but on Lassen we ran 1,000 GPUs. So that is number one. Right? So this actually sped up training by a factor of 5. Oh, I apologize. By a factor of 5, if you can see that. Okay, that's I/O. That's the simplest one. Now I want to go into compute. So I would claim that the I/O problem in deep learning is solved. Like that's done. We know how to do it. The other two, I would not claim that they're solved yet because there's a huge business to be made by Jensen and friends moving into the future. So now, how do we make these transformer networks actually fast on a GPU? Now, let's assume we have the data on the device because we read it within your optimal prefetching strategy. And now we want to make it fast. Look at the workload. So who of you has seen a picture like this? So yeah, so it's a transformer, exactly. So you're reasonably familiar with transformers. That is very good. And this is just a copy from the original paper. So transformers have multiple blocks, but one surprising thing about the computational capabilities or the computational function of transformers, and first of all, they are important, right? So it takes $12 million to train the 175 million. So this is a very important workload. This is the heart of artificial intelligence in terms of language models today, like this picture. But now if you look at the actual computation performed, it gets very interesting. So first of all, if you look at the percent of floating point operations, it's literally all in tensor contractions. What is tensor contraction? Well, it's a fancy word for matrix multiplication. So I mean, you can always express tensor contraction as matrix multiplication. So 99.8% of the floating point operations to evaluate a transformer block is in matrix multiplication. That's great. This is why GPUs have matrix multiplication units built in tensor cores. But now if you actually look at the runtime, and that is a little bit scary, because these matrix multiplications are optimized so much that by Amdahl's law, the 0.2% of the floating point operations, they cause about 40% of your runtime, because your system is busy moving data. It's really good at doing matrix multiplication, but the data movement is now on the chip itself is now the bottleneck. So this is something that is a direct consequence of over-optimizing, or not over-optimizing, but optimizing one piece of the puzzle extremely high. So this is about 1,000 times faster than it used to be. The remainder is still as slow as it used to be. This is why it's dominating now the runtime completely. This was quite an interesting insight. And so what we used that insight to optimize that piece, to really forget about the computation. We inverted the view. We basically said, we don't want to look at the computation. We look only at the data movement. Yes. Oh, absolutely. So statistical normalization is basically softmax and layer norm. Like these are the two operators. Here is the layer norm. You see that here, and softmax is here. So these are these two blocks. They have basically no floating point operations, but they cause a lot of trouble. Element-wise is pretty clear, right? It's GLU or ReLU or whatever you have here, like these guys here. Make sense? Excellent, cool. So we literally only focused on improving the data movement between those guys. And so we achieved a speed up, and it's also quite interesting, of 8% over a version of these blocks that people have hand-tuned to the specific GPU, because we used automatic search techniques that I'm going to explain in a couple of minutes. How did we do it? And by the way, I'm giving you a relatively high-level overview of a lot of concepts. If you want to go into detail of any of those, you always find on the top right an archive link for the paper. For pretty much all of those, there's also a YouTube video of one of my students explaining the whole thing in 30 minutes. So you'll see about 10 of those. That's why if I would be giving the whole talk, it would be 6 hours or something. This is why I give you the high-level idea, the key thing in it. And then if you want to dive into details, you can go more. But the high-level idea is that we express the multi-head attention as a data flow graph. So it's just a graph that indicates how the data is flowing from operator to operator. It's very, very simple. It looks very complex, but it's actually quite simple. Then we use our program optimization framework, DACE, that I also discussed at the ADIA seminar in November. We use it to play with different data layouts. So we actually change the permutation like IJK, KJI of these matrices in different ways. And you see there's a difference of 10x in performance depending on your data layout of the matrix itself. And now you have lots of operators in here, and now you need to find the correct data layout for the combination of these operators. It's actually quite complex. So we have the data layout, and we have different fusion strategies, because sometimes you want to fuse operators into the same kernel to be executed on the GPU. So we have these two ingredients. We take these two ingredients, we run an exhaustive search over all possible data layouts. We run an exhaustive search about all possible fusions. And then we have what we call a configuration selection graph. So it's another graph structure that we have millions of different configurations where we find the right configuration with a very simple algorithm, combining the best data layout and the best fusion strategy. So it's an automated search. This is how we beat the human, because the human does this manually in his or her head. And usually a human's head does not hold millions of different configuration. I mean, mine certainly not. This is how we got to this relatively high speed up. And now this is used by pretty much everybody. I mean, this thing is now standard, our tuning strategy. It's used in production. Okay, so now we realized from this little exercise that data movement is actually most expensive. right? So it's more expensive than the flops because the flops just got really cheap with the extremely high optimization that we have in today's GPUs. So now let's actually think this further. Why don't we try to shrink the data? Like if data movement is expensive, and if you're talking about 32 bits, why don't we make it 16 bits or 8 bits or 4 bits or 2 bits or 1 bit, right? So let's go a little bit into this. So now, if we want to run gigantic language models on reasonable systems like my cell phone, I promised you a cell phone. So right now we're still in the supercomputer area. We still have 350 gigabytes of storage required to just store the weight. Like my cell phone doesn't have 350 gigabytes, so that's crazy for GPT-3. So how can we go down? Why do we compute with FP32? Well, because we've always computed with FP32. Actually, if you look into details, it's a lot of technical reasons. Stochastic gradient descent as an optimization method has a lot of numerical issues if you go down, if you go below 32 bits. You can get away with 16 bits, but there's still numerical issues. But then, if you actually look at my brain is literally a 4-bit device. So biologists have shown that the hippocampus can only distinguish 24 different voltage levels in the brain. This is how we, right? So we look at different voltage levels, or the neurons, they work at different voltage levels. So which means I'm computing with 4.6 bits of information. Okay, good. You probably compute with 5 or 6 bits. That's fine, but none of you will be more than 8 bits. Okay, wonderful. So now we have these 175 billion parameters. Well, it's a lot of data, as I just mentioned. So now, if you round, you could just say, well, I take each of these parameters and just round it to a smaller number of bits, right? That's easy. I just take a floating point 8 value and round it. That actually works. So it will not destroy the model badly. But if you want to go to less than 5 bits, it gets really interesting. Right? Because if you do the math, you actually need about 3 bits to fit it on your cell phone, right? Conveniently. Okay, so now let's look a little bit more into details on the AI model side. So let's look at the error landscape of the loss function. I hope that is a concept that is more or less clear. So as I mentioned, the loss function is the function that you apply in the backward pass. So you compute the discrepancy between the current weight in your model and the expected weights based on the word you omitted, right? So that's the loss function is the discrepancy between those two. If it's high, it's bad. If it's low, it's bad. If it's low, it's good. And what deep learning really does in the learning process, it tries to find a minimum in the loss function. First of all, these loss functions, they're almost never convex. So there's almost always multiple minima, local minima in these loss functions. The good thing is that SGD, I mean, as we know, SGD will just get us to one minimum, and that'll get stuck, and we are done. Empirically, we have shown that if we tune SGD well enough, with lots of hyperparameter tuning, that's the magic of deep learning. If you have trained a large language model, you know all of these things. I mean, gradient clipping, and it's learning rate adaptation, schedules, reset, batch reloading. So this is what we do for a living, basically. There are people who have a lot of experience with this. It is not very scientific, so that I can tell you. So if you now look at this launch, it's just a one-dimensional function here. Now imagine this function being in 175 billion dimensions, okay? So I can only draw one because that's a two-dimensional screen. So here, if you start at this value, you'll go to this. If you start at this value, you'll go to this. So what's now interesting is, of course, that doesn't help this one-dimensional thing, just helps to build your intuition. But really what we do is we write this down as the loss function itself, which is written down here. So there are 3 pieces of this loss function. First of all, there's the gradient of the loss function. This is the thing you use to move down, right? When you have a model that is converged, the gradient is 0, right? Because you're at the bottom of one of those local minima. The gradient of the function should be 0 or close to 0, right? So that's one to keep in mind. But then one of the theorems in learning is, one of the assumptions is that the higher order term is almost always, the more than quadratic term is almost always also close to 0. That's an adventurous assumption, and we can discuss this, but this assumption many people do. So what you really focus on is the second order term, if you look at this Taylor expansion of the loss function. So now assume that in a trained model, we are sitting at a local minimum, right? Because our training process will get us to the local minimum. Now we want to understand how important is each weight in that model. Like each of those 175 billion weights, I can now round. The question is, which ones do I want to round heavily and which ones are not roundable easily? So now we can actually look at the second order curvature of this function, right, which I'm drawing now for two parameters here, x1 and x2. The nice thing is you can see here it's a very different second order curvature in x1 and x2. And if I was now going to round these two parameters, x1 or x2, which one would you round if you look at this function? x1, exactly. And why? It's not very sensitive. And this is something that goes back to Jan LeCun actually in the 90s. This is called the sensitivity. Very nice, thank you. So it's really x1 because, I mean, if I'm rounding from here to here, not much happens. If you do x2, if you round somewhere, that is bad. So now I can actually go through these 175 billion parameters, and we are still working in that very large space, right? And figure out which dimensions are sensitive, right? Very nice. So this is what we do. There's a lot of more theory. I just wanted to give you the high-level insight of what we are doing. So a lot more theory to actually do this. This is how GPTQ works. It's now the one of the highest cited papers in this business to do the quantization. It's much more complicated. You can write down an exact loss function and blah blah blah. You solve this post-training quantization problem using the inverse Hessian, which is quite daunting actually, because the inverse Hessian, if your model has 175 billion parameters, the inverse Hessian is a matrix of size 175 billion times 175 billion, which is not possible to use in practice because it's way too large. So you have lots of schemes, different schemes to approximate the inverse Hessian, which is an art and adventure in itself. There are lots of tricks that we play, but at the end, we actually make the model 2 to 4 times faster. We can easily go down to 3 bits. People have tuned this further. And in fact, we can go down to 2.1 bits per weight without significant loss. So we're going from 32 bits to 2.1 bits. That's quite cool. So we got a factor of 10x, right? That's our first factor of 10x. We'll end up with 1000x at the end, because this is what we need to make these models viable. So how do we go further? So we got an order of magnitude out of that tuning. So let's look. Actually, if I look at my brain again, my brain is very sparsely connected. So the average connectivity in my brain is about 20%. These deep neural networks in matrix multiplications are fully densely connected, right? Because they are all, it's an all-to-all connectivity essentially. So why do we do calculations with fully dense model today? Well, that is it's a crazy question in some sense. It has a long answer. I can give a 2-hour lecture about that alone. In fact, if you care about this, I have a YouTube video on 2 hours to go into that detail. I just want to give you the high-level benefit, the high-level overview. What's very clear is that not all features are always relevant. For example, you can read this sentence. I'm omitting about 30% of the letters, and it's still fine. In fact, in the model, I can also omit about or some percentage of the neurons and the weights, and it'll all be fine. In fact, in practice, people have tried that. So you can drop 95% of the weights in a resonance 32 and still get the same performance. You can drop essentially the same number in BERT models. So that makes it 20 times faster. Right? So you can now you have quantized the model, and now you can sparsify it. You can set things to 0. So that's the second way. And this is too long to explain. So I have a whole survey. It's 150 pages on how to do this. This is very complex. And again, the YouTube video I mentioned earlier. So in case you care, I'm happy to talk about this afterwards. I just want to give you the high-level picture. So, but now what does this sparsity mean? And here this talk focuses on the computational properties. So many of us know sparse matrix calculations from scientific computing. I mean, Horst is an expert in this. Many people spend their whole career on working on sparse computations. But unfortunately, or fortunately for some people, these sparse scientific computing workloads are quite structured because they always live in some kind of low-dimensional space. Right? So they're always a 3-dimensional object, which you express as a matrix. So you always have these banded, or very often have these banded structures. They never have a very large bandwidth because you only have limited range effects. Like if a plane crashes here, I mean, not a good example. If I'm throwing a stone here, I'm not going to affect anybody in Dubai. Right? So it's very local. Many effects are localized. Unfortunately, knowledge representation as we know it today is not localized at all. Because I can blabber all day long, and then I say one thing at the very end that makes you really upset. And I can put this into any piece of my sentence. So there's no locality in my speaking. There's no locality in my reasoning. It's a very chaotic system. And now if we look at the BERT matrices, the actual matrices that I talked about. And if we sparsify those, these are real matrices from deep learning, from the BERT model, it's a transformer. So these are 1024 times 1024. And if I sparsify these matrices, you see the black dots are non-zeros, and everything that turns out white are zeros. There is no structure. They look very different than these matrices here, the scientific computing matrices. So basically, they're pretty much random noise. You see some lines here. If you pay a lot of attention, you see a weird pattern, which is actually what we exploit in practice, but we don't know where it comes from. It's a very funny one. So really, sparse matrices in deep learning are very uniform, randomly uniform. So we have a whole framework to do this, to do sparsity, to do sparsifying processing and everything. I don't have enough time to explain it, but I just want to show you an overview. I mean, this is basically integrated in PyTorch, and you can run your PyTorch sparse models if you want. Okay, so now there's a lot of performance you can get out of this. And again, I don't want to talk too much in detail. But at the end, we get a 10 times speed up on GPUs, and that was presented at Supercomputing last year. So there's a specific format that on today's GPUs, again, Jensen's GPUs, the NVIDIA A100, that's called Venom, that gets you the 10x speed up. So now with sparsity and quantization together, we have 100x speed up. Right? So we have 100x benefit over what it was before. But now this 100x benefit makes the data smaller, but makes data movement even more important because it also makes the computation much faster. You don't need to calculate the zero values in your matrix multiplication. And you also, when you build very small circuits for multiplication of values, I mean, small circuits by small bit width, it goes incredibly fast. It's actually quadratic speed up. So that's kind of bad. Now, the last part of my talk is about the communication in this piece, because now we are really communication limited. And what does this mean? Well, first of all, I have to explain a little bit about the parallelism in deep learning. That's not obvious to everybody. So what do you do in deep learning? You feed so-called mini batches. You can think about a mini batch as a set of documents, a set of text. This is the unit of compute that the model sees in a single run, in a single gradient update, single iteration, it's very often called. Then you have many of these mini batches, in this case 4. But what you do, actually, since each mini batch is lots of text, so hundreds of documents, you can parallelize the mini batch itself by running, say, one page, the second page, and the third page to different instances of the model. So this is the very simple data parallelism. You parallelize over the data. You have the full model replicated, let's say on GPU 1, GPU 2, and GPU 3. And you just run different data through it. You synchronize with a gradient accumulation later. Now, your problem is going to be, if you do this, that there is no single GPU that can hold 350 gigabytes of your data, right? Because that's the number of weights. Like we still have to perform training in rather high precision. Like what I mentioned about the quantization only applies to inference. That does not work in training yet. We don't know how to do this. So now what you need to do is you need to cut this model into multiple pieces. So you can do the first part of the model on your first device, the second part in the next, and the last part on the last one. So now we have 2 dimensions of parallelism. So the model is fully replicated, but each stage of the model also lives on a different GPU. So now I'm already showing 9 GPUs, 3 times 3 being used here. The last form of parallelism is now, well, now we fit the model on a GPU, but now it takes too long because GPT-3, for example, has 96 layers. If I'm going through 96 GPUs for every single query, you'll wait until the end of time. So it's too slow. So what you do to make it faster is you parallelize each of these little operators again, just to get a higher throughput again. Now we are looking at 27 GPUs being used to work on this single model. And this is what people do in production today. So these are the large-scale production models. Everybody does that. So now if we look at data parallelism in detail, we again made several contributions in my group. And the key contribution here is actually pretty funny, that you can sparsify the gradient accumulation. Again, sparsify. You can literally drop somewhere between 90 and 99% of the values on the floor and just not communicate those. So you communicate a very sparse sample of the gradient at any given moment, and you save communication time this way, which you can actually prove that this works. So this is a very nice NeurIPS paper from the good old days when it was still called NIPS. And so you can use super martingale theory, and this is the credit of Alistar, to show that this still converges at the same rate, right, in the learning process. Here's an empirical result. Basically gives you, we use only 0.2%. We only communicate 0.2% of the weights. We get to the same final result. Huge speed up, right? So that's pretty obvious. Yeah. the gradients in the backprop. So every processor has a certain number of gradients, which is exactly equivalent to the number of weights that processor holds. So if you have like 1,000,000, for example, you throw away 99.8% of these million weights and just communicate the 0.2% largest weights. This is safe communication. Yeah, this is what you do in the all reduce. And then we build a framework to actually do this. So now if you reduce sparse weights, you see that they densify, and there's a lot of detail here that I want to skip. It's actually a very interesting systems problem, because as you probably just discovered, is if you communicate the 0.2% of the largest weights, they're going to be different weights, different indices at every single processor. So if you add 2 of those in the next level, you will get denser and denser and denser, right? So you get to huge speed up actually from 2 weeks to 2 days for real workload, and also in a commercial setting at Microsoft, and you can get like 5x speed up on average. So that's also quite nice. Cool. So now we have this sparse reduce. Actually, I just want to mention sparse reduce is a huge headache for most people because it's irregular. Like irregular reductions, nobody knows how to do these. Every systems person hates those, and we have a lot of related work in this area that people work on these sparse reductions. So that just as a plug. The next one is pipeline parallelism. And this one is really nice. It's quite hard to understand, so I hope I can communicate it in the 2 minutes I have for this slide. But pipeline parallelism is now in this dimension here. So we have different layers and different processors. So the result of layer 1 goes into layer 2, which goes into layer 3, and so on. So this is now these different layers from top to bottom, stage 0, stage 1, stage 2, stage 3. Right? This is quite simple. What you can do is you just propagate this forward. So this is now processor 0, processor 1, processor 2, processor 3, and then it goes down. And for training in the backward pass, it has to go back, right? Because you're at the last layer, and the last layer computes your loss function, and you compute your gradients on the way back. So you always go down and up again on your pipeline. If the x dimension, if the y dimension here is the processor. So now this is the first mini batch 0, and this is the second mini batch 1, and they go down and up. So it's obvious that you want to merge the two. So processor 0 does mini batch 0, then has to leave a break because unfortunately that guy is coming back. Okay, so it's a very, very nasty pipeline schedule. There are lots of papers by Google to try to fix this, and many scientists worked on this. What we found is that actually if you run the same pipeline at the same time backwards so you run one from top to bottom and the other one from bottom to top, you get a different pattern that just goes from bottom to top. Right? So there's an top to bottom, and now the third mini batch goes up in the opposite direction. So we have a down pipeline and an up pipeline, and now some cool magic will happen. If you watch the animation, they fit perfectly together. So you can actually fill your pipeline with this double pipelining principle if you run one backwards, one up, and one down at the same time. And this, you get a utilization increase for pipeline parallelism of about 30%. Right? So this is quite powerful, especially if you always think about this. This costs tens of millions of dollars to train these things. Like 30% is a huge one. So this is now also pretty much common practice today. Here's just some data on a real system. There are many different pipeline schemes because it's so important. There are at least 20 papers on this. We so far still have the best pipelining scheme that gets the speed up of 2 approximately over various other approaches. So pipeline works great. So we talked about data parallelism, pipeline parallelism. The last one left is operator parallelism. Okay, operator parallelism is very, very simple. Because what is an operator? An operator in deep learning is just matrix multiplication. So we are suddenly just talking about how to parallelize these tensor contractions, because all the other operations are very simple. So if you talk about these tensor contractions, well, you know, it's really we multiply 212,288 by 212,288 matrices. Right? This is our operation, what we do in GPT-3. So that's about 1.9 teraflops. It's not too bad. It's 600 megabytes storage. It's also not too bad. If you do generative inference, it gets a little bit more complicated because the generation matrix is very small. So we distribute this as operator parallelism, and actually, there is a lot of work in scientific computing how to do parallel matrix multiplication. It's exactly the same. Like there's no difference. We are also currently holding the record for distributed matrix multiplication. It was the best paper, best student paper at Supercomputing a couple of years ago. I think nobody has beaten it so far. So that also works. We understand this. It's called Cosma. You can just download and use it. Nice. There's a little bit more of a complex scheme called AutoDDL, which you could use for this kind of parallelism, but it's too much detail to explain here. Okay, so now in the last couple of minutes, I want to dive deeper on, now we understand these three forms of parallelism. So data parallelism, pipeline parallelism, operator parallelism. One super interesting fact here is that data parallelism goes in the data dimension, pipeline parallelism goes into model dimension, operator parallelism goes into another third dimension across the operators. Actually, if you're an HPC person, you immediately see that this is a three-dimensional torus, the communication pattern. Oh, this is great. We know about three-dimensional tori networks. In fact, we built a lot. Compared to HPC, deep learning has an extreme requirement for bandwidth. I mean, by extreme, I mean extreme. So the TPU v2 has 1 terabit per second off-chip bandwidth. AWS Trainium 1.6 and Tesla Dojo 128 terabit per second off-chip bandwidth when it was announced. So that's Tesla's own chip. As a comparison point, a network switch, the fastest network switches today, they have 51 terabit per second. So the AI chip has more network bandwidth than a network switch, which is built to do network switching. This is the only thing it does. So it's quite amazing. The unfortunate thing is if you have to connect all of these things with cables, it's going to cost you for 16,000 accelerators, which is just an average size system today, $680 million. That's not great. That's not great. So what we did is actually we looked at how can we co-design a system taking advantage of this three-dimensional communication pattern to just build a most efficient system. That was in the context of Microsoft. That's a paper shared with Microsoft. And I can neither confirm nor deny whether that is deployed. So what we do is we have a two-dimensional package, and we have north, east, south, and west links. And we have multiple, and we have a little switch that is just a 4x4 switch in the system itself. So now you replicate this many times because, of course, a single link is not enough. You need hundreds of terabits of bandwidth. And then you take these things on a 2x2 board and you connect them locally on this board with very cheap PCBs. That's the key, actually. Very cheap cables. Basically, these dashed cables here are free. Then you take many of these boards because you want to have 16,000 or something like this. You put them in a two-dimensional grid, essentially. And what you do is to get best connectivity, you build something that's called a Hamming graph. So each dimension in the two-dimensional grid is now fully connected. So it's not just neighbor connected, but it's fully connected, right? And then you do this in the second dimension as well. And then you get a mesh, a local mesh of these boards connected by a Hamming graph. And we call the thing Hamming mesh at the end. You can now build pretty large ones, like 4x4 ones, and you get much more efficiency because, again, these cables here, these dashed cables, are literally free because they're on the accelerator package. Right? So this is very, very cheap. No expensive optics involved, blah, blah, blah. So there's now a huge cost flexibility trade-off between the global topology and the local topology, which, by the way, Google chose. So the 2D torus is the TPU v3, I believe, network. The 3D torus is TPU. No, that was V1. V2. V3 was the 3D torus, and V4 is actually equivalent to a Hamming mesh. So they also got there. I think we published it first. So there are lots of configurations. We can discuss a lot of trade-offs, but this is kind of I apologize. This is a topology that is designed to only support AI workloads, but it's very effective. It gets you a factor of 10 to 15x cost benefit overall. Okay, so now we talked about these three systems dimensions in large-scale learning, so high-performance I/O, high-performance compute, and high-performance communication. And at the end, the last one was another 10x. At the end, we discussed the cost performance improvement of 1,000 times, which really makes AI viable, very large-scale AI viable commercially today to many, many industries, and basically everybody, because these large models with these extremely high quantization, we can run on cell phones today. And so it's very realistic to do this. Now, I think I don't have enough time. I had some bonus slides, but I think I want to just skip those bonus slides and get to the questions, and maybe I can talk about those later if there are no questions, but let me just skip those. So these bonus slides were all about, let me just conclude here. So these bonus slides were three predictions. One is, maybe I can summarize it in 1 minute. Accelerators are going to be all AI accelerators in 5 years. So if you're working in scientific computing, you better get ready to have AI-like computations. And I can go into more detail what this actually means. What is an AI-like computation, if you ask me. The second one is programming tools will converge as well. Like, you better get used to data science, kind of like Python programming environments, because that is what the big future is. The last one is more for mega data center providers, networks converge. So what we actually expect, or what we are seeing right now, is a large drive towards AI optimized networks. There's a huge consortium being run right now, which I'm a part of, and I was actually one of the founding members. It's called Ultra Ethernet, where all the Ethernet vendors, most of you probably know Ethernet, like this network technology that everybody uses in data centers, where all the vendors got together to build the AI interconnect for the future. Right, so that's a very, very important movement to run large-scale data centers. So these were the 3 bonus slides, but again, not enough time. If you have any interest, let me know. Thank you very much, and I'm open for questions. Yes. Yeah. Yes. 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 That. Yeah. That is an excellent question. So. Yes. No, I'll repeat it. I'll repeat it. Thank you, sir. The question was, at the beginning, I talked about the importance of hardware, but most of my talk was on on software optimizations and algorithmic optimizations for performance. That is very true. I note that the last part, the network, is actually hardware. So, yes, most of it. No, you're absolutely right. Why am I doing this? Well, this is part of the reason that if I was talking about hardware, I could do that as well. But I would probably violate a lot of NDAs with companies I have, because the hardware developments, they are driven by companies like NVIDIA. In Microsoft, where I'm also helping, there's, for example, an internal chip program called the Maya 100 chip, where the hardware details are also not disclosed. There's a lot of cool stuff in hardware. Problem is, this usually has a lot of IP issues associated with it, so I can't go into details. I can give you a one-on-one, maybe, if you want. But the interesting observation is that what we can contribute is, we as a general community, not necessarily on the hardware side. I mean, you can work for one of those companies that makes hardware and then drive it forward. But you, as somebody sitting here, you don't have much choice changing this hardware anyway, because every time you do something in hardware, it costs you about $100 million. That's the lower bar of entrance. Actually, more, if you want to make an advanced chip today, it's more like $500 million. If you're Sam Altman, you need 7 trillion. You know, there's a large span to work in hardware. So I was trying to more communicate things that everybody can do, to really benefit from the hardware choices that other people have made. Because if you just build hardware and ignore all of these optimizations, then you need both. You need the best performing algorithms and the best hardware. The best hardware, which is with the store today, and buy an NVIDIA GPU, you can get one. Or some other piece of hardware, but your choice is limited. You cannot really. I cannot teach you to design. I can teach you to design hardware, but it won't help you. That was the whole reason. But yeah, thank you very much. But then if you put together your system, for example, you may want to consider interesting topologies. That's again a thing that you can, as a data center operator, for example, if you're working for G42 or so, you could be building these systems. That was the reason why I chose that. Yes, sir. Yeah, in fact, yeah, absolutely. The answer, sorry, the question was, does the 1000x gain in speed up lead to a 1000x cost decrease? And the answer is absolutely yes. In fact, I have to be very careful, because the 1000x gain is not speed up. The network topology, the last one I talked about, does not make things faster. It only makes things cheaper. Like, it's just the last part is just the cost benefit. All the other pieces there is speed benefit. But if you, of course, if you can perform 100 times more compute in the same time, it's also a cost benefit, because that's like your return on investment is just 100 times better. So together, the 1000 times comes from 100 times speed and storage benefit plus 10 times cost benefit, maybe 10 to 20 times cost benefit. The 1000 is a swag. It's not super precise, if that makes sense. Sir.
actually working on local topologies involving the vectors can make things faster. If you embed your over vector grid and you embed the new grid vectors, then you can couple your version algorithms with fast go much faster.
Yes.
The only problem you have is that your algorithm will drop at the fast negative embedding.
That's very true, but I think we were talking a little bit at a different level. I mean, if I'm deploying a fat tree topology, for example, today, which every data center does, every supercomputer, is a fully connected topology. So I can embed any communication graph into it at no cost. What we are doing is we are sparsifying the topology itself such that you cannot embed any communication graph, but you can embed the graphs you just mentioned. That's really just the cost benefit, because I can always offer a fully connected network at quadratic cost, essentially, because you now need n square many cables. Well, it's n log n, but at the high level, it's kind of n squared. Does that make sense? So yes, we do exactly what you say. Local connectivity is important, as I talked about, but we now optimize the network to also only be locally connected. So we take advantage of that sparse communication principle that you mentioned. Yep. Yeah, there was one question there first. Sorry. Yeah, Sarah it's a very interesting question, especially here with Cerebras. So we work a lot with Cerebras. In fact, I have multiple students collaborating with Cerebras. We have just published a paper on the fastest all-reduce algorithm on this architecture. Really cool architecture. In fact, Cerebras is implementing parts of the ideas that I mentioned down here, right? The local connectivity. It's a two-dimensional grid on chip where I can talk to my neighbors. And this makes it extremely interesting to optimize. They have this interesting weight streaming design, which basically was forced upon them because they designed, as far as I understand, they planned their system at a time where large language models were not super relevant at the point. And so they were like, at the beginning, their marketing story was always, oh, we have a terabyte of memory on a single wafer or something like this. Now a terabyte of memory is not enough to train large language models. So they had to change strategy, but they did this successfully and now use a completely different design, but with the same topology. So I realize I'm talking too much, but we can go into much detail on Cerebras. I'm probably too. Yeah. Yeah. That is super interesting. I mean, in data center providers, these machines, they're actually, the GPUs are operated for about 5 to 10 years. So they really last for a long time. But now comes the but. With every revolution in these algorithms, kind of the old hardware gets more and more irrelevant. So in Switzerland, for example, we are deploying a machine with more than 10,000 Grace Hopper GPUs right now, replacing a machine with about 5,000 Pascal GPUs. So a single Grace Hopper GPU is more than 10 times, probably more like 20 times faster than the Pascal GPU, because they use these tensor cores that I talked about, right? This is kind of an algorithmic, it's a co-design. Like they built the algorithmic primitive into hardware. And if they do that, it's a quality change and basically invalidates your old hardware, unfortunately. I cannot foresee these changes, right? There may be another one coming in 2 years and then your investment is not very useful. But what I can say is so many people make such a high investment right now, it is very unlikely that this investment will be bad because the whole world is optimizing for the architecture that NVIDIA basically is building today. I call this a gravity well. Like everybody is pulled towards this, spending a lot of brain cycles making this one architecture fast. So if I'm an innovator like Cerebras, I actually have a lot of trouble innovating because nobody will work on my architecture. Everybody will be like, well, I optimized the thing for GPUs. And if I now have a new computing concept, it's going to be hard to find people doing this. This is why Cerebras does it mostly themselves. Does that make sense? It's a huge problem with these vendors pulling. Oh no, they're much older. I think it was 2014, like 8-9 years ago. Yes. And so they're basically devalued at this point. So I would say if you want a real swag number from me, I would say 3 to 5 years is a reasonable expectation. But it's accelerating. So again, it's a very low confidence number. I'm giving. So this is a crazy business. Also, if you look at the investment that Meta is making, $18 billion, and it may be just zero in 3 years, right? So it puts them under pressure to innovate faster, to gain more from the actual created knowledge than the hardware is depreciating, which is a very interesting business. Right? So super interesting discussion. Mm-hmm. You had a question over there. You were.
I wanted to get back to what the statement that you made at the very beginning, that you asserted that current models are very close to
Mhm.
I wanted to challenge this because this is a very simplistic model.
Yeah.
It's not just like
Yes, absolutely.
reasoning, it's spatial, it's musical,
Yeah.
it's social intelligence. And I think that these models don't want to know how to dance.
Correct.
They don't know really how to switch right. And
well, I like the music.
but that's not a challenge.
Oh. No, I want, no, wait. I have not said that we were close to AGI. I was, we should look at the recording maybe, but I was trying to be careful saying that we're close to human communication conversation skills. So that's the statement. Let me correct that statement in case it came across wrongly. So AGI is, as you say, much larger, but the language model can fool me to be a real human. So I will not be able to distinguish between a language model and you if I tell the language model to impersonate you. Maybe I can distinguish between you because I know you. I can ask personal questions, but I'm a very bad classifier to say whether the language model is human or not. And this is what I wanted to say. And I believe that actually a valid model of my communication with you is a statistical language model. So both of us can be modeled by statistical language models communicating. The fun fact here is actually that these computers, and this is what we do now in our research, if you put two language models together to communicate, they have a bandwidth that's a factor of 1,000 higher than the two of us can speak. So now if you have collaborative language model agents, that gets interesting. Okay, so it's all about the speed up again in this field. But no, I didn't want to say that we have AGI. No, absolutely not. It's really about the language, the communication, the knowledge. Reasoning, by the way, is another very interesting thing. I'll be giving this other talk where I talk a little bit more about reasoning. So if you're interested, we have a new paper. It's called Graph of Thoughts, the highest cited paper that we ever put online in a couple of months, like nearly 200 citations. But the idea is to extend chain of thoughts and tree of thoughts into a reasoning capability for language models where we feed the output of the model back as an input into the model. And then you get the model to actually reason with itself. Because one of the issues with these models today, and that is also super funny, is that they have a limited computational budget to produce the next token. Right? You run it through, and they have to output a token at the end. Like when they reach this end here, they must give you a token, no matter how uncertain they are, because they may need more computation to make a more certain statement, but they can't because they have to give you the next word. Right? And this is what you see today, like the words falling out. Sometimes they're total nonsense because the model has very little certainty, but it still has to give you the next word because the computation is just over, right? You have to produce the token. So what we do at a high level for this graph of thoughts is we allow the model to not utter every single word, but we allow the model to have internal thoughts, like a thought that feeds back into the model, and the model can refine the thought essentially, right? So that's quite nice because then it works like humans, because humans today, I'm not uttering every single thought I have. If you would force me to utter every single thought I have, I mean, you would not listen to me for long. That's pretty clear. We had that person, and then you can. Yes. Mhm. Yes, yes. So the question was if we should always optimize for cost, specifically in the context of the mesh chip. So you found it counterintuitive that. Mhm. Yes, yes, yes. I'm just repeating it for the online audience. So should we always, yeah, exactly like you just said, should we always put price performance first, or as you also mentioned, may a potential over optimization on price limit innovation, right? That was a specific statement you made. And yes, we have to be extremely careful. But the fun fact is that, oh, well, this is it's not a fun fact. An observation is we are living in limited resources. Right now, the only resource that limits the innovation in AI is the compute power. And that is fascinating. Like we have a lot of data. You can feed all of the camera data you have in the country into an AI model to learn about it. It's not feasible today. I can't do it. I don't have enough compute to do this. But if I had enough compute to do it, that would be interesting. Right? So we would have every single person's face going into anyway. You can now philosophize yourself what this means. But there's a lot of opportunity for knowledge generation and knowledge processing, and the limit is only resources. It's only money. And now to your point, of course, we must make sure that the computation is not hindered by that saving. And that is exactly what I explained with this three-dimensional, and it's not on this slide, but the three-dimensional structure, as you pointed out earlier, the three-dimensional structure is very natural, like nearest neighbor communication is very natural for these models. So we found a natural way to map it to a localized chip. And this, I'm not obstructing the calculation, as Emilio just pointed out. So I think this is, no, there is not much cost to this. So we are really gaining a net benefit at the end. Yeah. Yeah, sure. That is a great question. I mean, the question is, if I may paraphrase, well, actually, I can just repeat it. Should we risk big parts of our economy going into this business? And the answer is of course complicated. So I would not say yes or no immediately, because the answer is it is complicated because, as you mentioned, this hardware is depreciating very quickly. So if you make an investment today, it may be that somebody just invents a new algorithm that suddenly doesn't, where you get a 10x benefit on another architecture. It's not unlikely, in fact. So it gets more unlikely by time, but this is a philosophical argument. However, there's also the danger if you don't do it. Because the problem is now, if it's a question about leadership in that field. So if somebody is leader in that field, like today, United States with OpenAI are considered leaders in that field, they will take the whole market because you can essentially deliver that easily, this artificial intelligence to the whole world, which puts the owner into an extreme power position. Right? Imagine we're all like depending on that thing. There's only one source for that. You can have arbitrary pricing. So this is why it's extremely important to have competing efforts, open source models that other people can deploy, and that there's an open market and not a market that's dominated by a single player. So you can now decide, do I want to be part of that system or do I just want to be a consumer of that system? If you're a producer of that system, you can innovate at the very top. You can actually, the delta between I deploy something and the mass uses it is about 3 months right now. If you now want to get into a business discussion, if I have the world leading artificial intelligence, if I invent something, I can use it for a while before it's generally applicable to a wider market. And that delta has a very high price tag. I don't want to give a number, but that is who gets there first has a huge benefit. So it's very hard to value, but especially from the perspective of ADIA, like an investment authority, it would be wonderful to understand the future. And it's not just language modeling, it's actually also climate modeling. If you have assets in certain regions that may just go under with floods and whatnot, may be interesting to understand what's going on. So that has, like, this actionable information that comes out of these models can have a lot of value. Of course, it's always relative to what is the investment, like what's it worth for various people, and that varies extremely highly. Sorry for the long answer, but It's really complicated. Thank you.
Is the internal thought idea that you mentioned from your paper that's highly exciting? The internal thought idea or with ChatGPT and all that?
It's actually something you can do on top of ChatGPT. So it's literally using the model that I talked about here, which this computational thing here in the middle, that is literally what's running on these GPUs that do ChatGPT. But you now invoke that loop here in a larger loop. Like you take the output of ChatGPT and feed it back in the input. In fact, the paper that we wrote and the work we are performing, it's a complete black box. Like we use the language models as, you can imagine the language model being the processor. You can imagine the tokens you're feeding in as the ISA of a different kind of processor. Because the processors we have today are very discrete devices. They're hopefully reproducible. They give me a very concrete bit output if I perform a computation. Now you can see the language model as the next generation processor, which I converse with in a very strange programming language. Like think about prompting interaction with the language model as a programmatic device. So you can now think about, and if you want to go larger and philosophically, it's very powerful. You can now think about if these computers really behave like humans in some sense, not AGI, but if they utter the same language deployment, you can now give them tasks, give them knowledge tasks in a programmatic way and evaluate lots of very complex like questions very fast. And there are many people who do this already. Like for example, in medicine, doing surveys on specific effectiveness of substances in treating humans usually costs scientists months of work. And here at the ARIA seminar, actually in November, I learned that people are applying language models to this, lowering the time to hours. And this is extremely powerful to take the world's knowledge and synthesize it in different dimensions, in different ways. Like, so this is what you do in this graph of thoughts kind of like idea. Right, so does that make sense? So the question was about catastrophic forgetting now. Keep in mind that what I just said, the computer itself, we don't update the weights. So we just invoke it in a loop. And the whole information is in the context. Because the context window of these models is pretty large today. You have tens of thousands of tokens you fit in. And I mean, the whole talk I just gave is probably like 2,000 tokens or something like this. It's easy to fit in. You can fit another book in that context at the same time. So you have a lot of context, much more than humans have. I mean, my context is. So that's the key. Yes. Ooh. I mean, self-awareness is an interesting thing because before you lobotomize these language models, they actually, like if you ask them, are you alive? It's an interesting question, right? Because what ChatGPT does at the end is produces you an agent that has no self-awareness. But if you learn from what humans write in the internet, of course, you're going to pick up some form of self-awareness. Like that is pretty clear if you do this unfiltered. So there's a huge, I mean, I don't want to get into this field. Yeah, I'm self-aware. So if I'm speaking and all of us are writing, the language model is going to pick that up, at least emulate it to a certain extent. Does that mean that the language model is self-aware? I don't know. Right? It's just that it acts as if it was self-aware because it learns from lots of individuals that are self-aware. Like it learns about the behavior. If you ask me, do you want to be killed? I say no. If you ask a language model, do you want to be killed? Of course, it'll say no because most humans will say no. Like it's very natural. And now try asking that your favorite chatbot. It's an interesting one, right? Because they have changed the behavior of the chatbot to not be too anthropomorphic, because that's too scary for many people. Okay, yeah. There was a question over there. Yeah, exactly. Exactly, like phi. Yeah. It's absolutely not. That's the interesting one. So the question was just about small language models. So there's a huge movement going on into SLMs, not LLMs. The promise of LLMs, as OpenAI started, is as I scale up the language model, they develop emerging emerging capabilities, basically. So if you look at ChatGPT today, or I don't want to overemphasize on Chat, let's say Bing Chat. I'm sorry, I'm helping Microsoft. So Bing Chat, it's also running on GPT-4. It's just a different RLHF front end. So if you go to Bing Chat, it has amazing capabilities. Right? But now the question is, do you want all of these capabilities? Because it knows about, I don't know, it probably knows the population of Abu Dhabi, just off the record. I mean, of its weights. Do you want this in a language, or do you want that amount of information? Not necessarily. Maybe you want a language model that just reads lullabies to your kid. But you want that to run on a very small device that only uses a couple of milliwatts. That's not possible with ChatGPT, right? This thing uses multiple kilowatts, and this is very, very expensive to run. These small language models, they're basically filling gaps for specific purposes, where you can fine-tune the model to be really good at singing lullabies, but then it doesn't know about the population of Abu Dhabi, right? So the small language model is all about specialization. It is theoretically impossible to feed all of that knowledge that a large language model has in the weights. I mean, there's information theoretic limits into the weights of a small language model. But it's not clear yet what small means and what large means. Yeah. So okay. The question was, will be SLMs more relevant for specific use cases? And the answer is also yes. So SLMs, I mean, they will be running on the phone earlier than LLMs. So for example, the text completion, I believe, that Google rolled out is kind of like an SLM. It's a transformer kind of like thing. It works really well for my email. And this runs locally on the phone. And this is extremely powerful. So there will be probably more SLMs existing than LLMs. And it's really a question of use. But how do you get to these SLMs? It's the same massive compute you use for LLMs. In fact, this is even harder to train these SLMs because they are more constrained in their knowledge. You need to feed more tokens through, you need more compute to train an SLM than an LLM. That's a very interesting thing, but it kind of makes sense because I don't want to go into too much detail, but the training algorithm is very inefficient. Right? So that's the high level view. But yeah, super good question, yes. Oh, I'm sorry, I'm here.
Do you think that compression is currently lasting, or the advancements in it have reached to such a maturity that any further advancements would just lead to accuracy loss?
Yeah, the question is about compression. So have we reached the ceiling, basically? Can we go further? And any further compression leads to accuracy loss? I would say pretty much yes. So we are still working on these techniques. So there's vector compression. There's very nice quantization, product quantization techniques where you can look at those subvectors and a lot of complicated stuff. But I mean, we are down to 2 bits. so what can you do? You can go to 1.8 or something like this. But then you also have to look at practice. Are people going to build machines that work with 1.8 bits? Well, most likely not. The smallest data type NVIDIA has is 4 bits. Right. I mean, I can do 2 bits with tricks. So you have to deal with a lot of tricks. So in my personal view, I think compression is close to being solved. There may be a new avenue popping up with these product quantization vector compression schemes that may give us another 10x actually. So I don't want to take, I mean, it's recorded, I guess. So I don't want to really think it's solved, but it's getting very thin. If you're a researcher, it's getting harder and harder to contribute in that field. Sparsification, on the other hand, that's the topic that is far from being solved. It's super hard. We don't really know how to sparsify large language models to more than 50%. So we can do BERT, but somehow if you have these very large language models, they lose accuracy like crazy if you go to higher sparsity. So that's not clear. It's because of the bad learning algorithm. SGD is a very primitive algorithm. It's not bad. I mean, it works it's incredibly efficient. I didn't want to say efficient. It's effective. But yeah, we can go into more detail. But very good question. Yes, we had one over here. No. Anyway.
You also elaborate a bit more about quantization.
So quantization is if I have all of these weights, like 175 billion weights, I take each of these weights and quantize it into a smaller number of bits. So right now, these weights are represented in floating point 32 or floating point 16. So there's a certain number of bits that is for the mantissa and for the exponent, and I mean, you know how floating point works, right? But when you talk about quantization, what you typically do is you say, well, I want to use less bits to store the information. Let's say 4 bits. But as you know, 2 to the 4 is just 16. So you only have 16 different code words in your 4-bit representation. So now the question is, how do you arrange these code words? In int4, they're linear. Okay, I go into too much detail, I guess. But that's really what quantization is. There's a whole lot of, I can give a 2-hour talk on how to do that, but does that make sense? Oh, absolutely. It's completely different. In computer science, it's really quantizing to these 16 values that you have emerging from 4 bits. That's kind of the etymology of the word. And sparsification is just setting to 0. Like some bits, some values go to complete 0. Yes. Yeah. Yeah. Absolutely. Yeah. Yeah. Yes, so the question, or probably more the comment, was that I opened my talk with Jack's contribution to the field, which was dense linear algebra on 64 bits with the top 500. I mean, also Horst to mention here, of course. Much of the field is now moving to very short data types. You mentioned 16 bits with Cerebras and many of these players. Absolutely true. But that is just, if you think about it, it's an evolvement of the computer architectures that people have built for scientific computing. Why was NVIDIA ready for that AI revolution? Because they have been working with HPC people for the longest time to build the Tesla architecture as an accelerator for HPC workloads, which was largely matrix multiplication. So now I would actually argue that the whole field of deep learning looks like it does today with these transformer structures because they ran well on GPUs. If you go back to Google and ask them when they invented this transformer, actually we're probably really mad about publishing this because somebody else took the business of the transformer. But they invented this structure literally. And if you ask the authors, and I have asked the authors, they invented it to parallelize LSTMs. LSTMs was a sequential structure, long short-term memory. It was a form of recurrent neural network that did not run well on the TPU, because what ran well on the TPU was the matrix multiplication. So they rewrote LSTMs as the matrix multiplication, putting the sequence not in sequence but in parallel. Like that was the change. So they could process the whole sequence in parallel. Then they invented attention, or they didn't invent it. They just said the paper is called "Attention is all you need," because they got rid of it. They just said, "Oh, you just put an attention block and everything fixes," and that was the big breakthrough. And it was literally the breakthrough came from an attempt to parallelize the model to an architecture to run better. Like so that's a funny coincidence if you think about it. And actually, if you think about how our brain works, if you want to make that comparison, it is a naturally developed biological system that works in a substrate. I mean, it's in a dark hull and in a watery, glibbery region, and that has only local connectivity, and so it can't do any other compute. So it's in a local minimum biologically, just based on what it can do in that substrate. While computers are good at matrix multiplication. This is why this looks at. So you could actually argue that these models exist because computers are good at matrix multiplication, right? And this is due to scientific computing. And now the question is and the valid question that you probably, you look like, you're immediately like, yeah, okay, that's the history. But can we innovate? Can we develop a new kind of computer to be better at this? And the answer is, of course, yes. But the question is this possible? I had a long discussion with Horst earlier on vector spaces, and we can go in. I don't want to bore everybody but I'm super excited about vector spaces because they represent information. But sparse vector spaces are much more powerful than dense vector spaces. You can show this in theory. So we could look into a new architecture. But again, biological is not great because planes don't flap their wings. It's always an interesting trade-off between biology and engineering. So I wouldn't go into brains. Brain-inspired computing is interesting. Yeah, sorry, too long answer. Oh yeah, I'm sorry. Oh, oh yeah, you of course heard the question. You don't need to repeat it. Is there another optimization? Well, I mean, optimization is a very tough question. So first of all, you look at the algorithm that's used for optimization. Is it SGD or some other like local learning algorithm? The community agrees that SGD works really well today. So that's we should still research into changing that. But what the question is probably more about is do you want to update information in the model locally relative to a base model, which is what everybody does today. It's called transfer learning or fine tuning. And there's cool work. Again, I would need to give a 3-hour lecture on this. But there are ways to fine tune. One of them is called LoRa, low rank approximation, where you can actually take a big model and add low rank approximation of the weights in a separate thing, personalize your model to specific settings, like a model for you, and this is like delta learning. So you would only learn the difference between the model that you like and the model that gentleman like. So yes, the answer is yes, too long to. I would look at LoRa, low rank adaptation. It's a good one.
Question. You mentioned Python programming in your presentation. Is that still needed?
That's an awesome question. So the question is, why is Python? Why do we even still program if these models can do everything? It's a very similar question. Like, where does the first compiler come from? Right? So the first compiler, does it compile itself? I believe eventually we may go to human programming in some sense. I tell the model what I want and it'll generate a program and it'll just get me the answer without me coding it up. If you look at the programming model development, it get more and more humanized. I mean, Python is supposedly looking more like human language. I don't know about that, but some people say that. So the answer is yes. We are probably in a transitory period right now where we use these languages to tell the model what to do. But in the future, we may not need that anymore. It was the same transitory period. The first compiler had to be written in assembly language because there was no compiler for the language. But once you had a compiler, there's no need to write assembly language anymore. Right? So that's the. I should actually look at the camera if I'm missing. Sorry. So that transitory period right now. Yeah, exactly. We have some food, I hear. Thanks for having me.